Hello and welcome to another revision session for physics, AS level unit 1, electricity part 2.
Dash C.
I don't know. Okay, I'm Will.
And I'm Connor, sorry, a bit delayed there.
I am very much the mathematician to this outfit, and Connor is very much the special scientist.
Special.
Today we are going to be just dusting off electricity as quick as we can.
Killing it quickly. I'm rising.
We're going to start with potential divisors. Connor, you can take this one.
Is used in circuits to divide up the supply voltage, often to enable a circuit to respond to other factors like light, levels or temperature in order to control a device like volume. Basically, in a very broad way, you have a circuit with two resistors, R1 and R2, and the voltage out from R1, let's say voltage across R1, if you have the proportion of the resistors' resistances in proportion to the total volume, so say you've got 3 ohms out of 12 ohms, it's a quarter, and if you have 12 volts, it'll also be 3 volts because it's a quarter. It's proportional. Don't look at me like that.
Okay, I'm just trying to listen to put myself in the position of our viewer. Hi, Connor's mum.
Hi, Mum.
Because that wasn't making sense, but I do get it. Yeah. So what we're talking about is those diagrams where you have sort of two. You have a normal circuit, but then you have two resistors, and you usually have a V out coming out of the second one, or a light bulb or something like that on the second one. And yeah, what kind of said it exactly just right, because the voltage is split over the two resistors. It's proportional. So yeah, basically, it's proportional. The resistance, if you have resistance Y, which is like a bold line, then the resistance Y, because the length is proportional to the resistance. So L1 divided by L1 plus L2 equals the voltage out divided by the voltage in. It's very hard to explain.
Yeah, it makes more sense when you see it in an exam paper.
So moving swiftly on, potential divisors in action. You can do this again, Connor. I'm not. This isn't my strong point.
A thermistor can be used in a potential divider to provide a device that responds to temperature variation. Sorry. As the temperature increases, the resistance of the thermistor falls. This means that the resistance of that thermistor takes a greater proportion of the voltage drop.
The resistance.
Voltage. As the temperature increases, the voltage out.
No, the voltage output would increase.
Yeah.
Yeah.
That's
basically a good way of thinking about it. If you didn't get the first bit, is if you've got the two resistors in series, then if the first one's a thermistor, and as the temperature increases, then the resistance falls. So a lower resistance, which means that the resistor takes the second resistor takes a greater proportion of the voltage drop. That's the easiest way of thinking about it. And the same thing happens with a light-dependent resistor, I believe, Connor.
In an LDR circuit, light-dependent resistor, as the light levels increase and the resistance of the LDR decreases, and so does the potential difference across it. If a lamp were placed across the voltage output, then it would be illuminated when dark and switch off when light. Conversely.
Yeah. The key, if you're not really understanding that, then the key point is that this time the fixed resistor is the first part in the circuit, and then the light-dependent resistor is the second part in the circuit. And yeah, obviously the current is the same over all of them because it's in series, so that doesn't matter.
Moving on.
To electromotive force, I can do this, or EMF. EMF is defined as the energy transferred per coulomb to the circuit from the battery or the power supply. The EMF of a cell can only be measured when no current is flowing. The EMF, that's the voltage. E equals, it's like a squiggly E. I don't know what the name for it is.
It's almost a backwards 3. I'm not sure. I think it might be. Anyway, it's a backwards 3. Let's just say.
Just do a wiggly E. Equals W, which is work, which is the energy transferred, in joules divided by Q, which is the charge in coulombs, because obviously it's energy per charge, energy transferred per coulomb. So, it's pretty self-explanatory. Internal resistance?
All real cells and power supplies have their own resistance, called internal resistance. This is given in the equation, this is a bit long. Volts supplied, which is the EMF, which is a backwards 3 or squiggly E, equals I times capital R which would be the voltage lost by the circuit. So it's it's sort of substituting in V equals IR. So you've got V equals IR with big R, which is the voltage lost in the circuit, and then you've got plus I little r, which is the voltage across the internal resistor. So the small r stands for the resistance inside the cell itself, which is usually given as the cell right next to a resistance labelled with a small r, and then that is surrounded by a dotted line. That's usually the annotation they use, or the notation they use rather. So you can rearrange that equation to give you E equals I times, in brackets, R plus R, little and big, yeah. Or you can have E equals V plus IR, because V equals IR. Just substituting in equations comes into a lot of this.
Yeah, just the easiest question will be they give you the internal resistance and the electromotive force, and then you just sub that in, and they ask you what the voltage is across the whole circuit. So you'll sub that in for, you sub in little r for the internal resistance, you sub in the current,
yeah.
And then take that over the other side of the equal sign so it becomes a minus, take that off the electromotive force, and that will give you IR, which is V equals IR, so it equals V. So your answer will equal the voltage across the whole circuit, across the battery, across the whole circuit.
Whole circuit.
Another way of saying it is across the battery, if it's because it's one side to the other side, it's like the whole circuit. Right. AC electricity. In metals, the charged particles responsible for the current are electrons, which move randomly at high speeds, even with no applied voltage. The direct current is produced when electrons all drift in one direction whilst continuing their random motion. So, like the net movement, if you like. An alternating current is produced when the drift velocity of the electrons constantly changes direction. Electrons oscillate when in an alternating current, or when an AC current. Again, think of the year 7s in the corridor with the year 11s, even though that was in the last audio thing.
Yeah.
You should have listened to it. So it's like, instead of the year 7s, imagine a whole load of them in this corridor, and they're sort of bustling about and knocking into each other, and the net movement in a DC is gradually, one is pushed off throughout the other end of the corridor.
With an AC,
even though they're moving so slowly, the net movement as they all bump into each other like dominoes
is instantaneous.
Yeah. But with alternating current, they're sort of
running in both directions and then just turning around.
Yeah, they're sort of running, trying to go to all different classrooms, and then like the net movement is sort of forward and backwards, but it's almost like it's still energy.
Another analogy I heard was putting marbles in a tube. I mean, if you fill a tube with marbles, and you push one into the end, one will pop out the other end instantly, but the movement is very slow. It's about, I've heard it's 30 miles an hour if it's electricity. So, but AC is like you're constantly pushing marbles in both ends alternately. So it's sort of marbles going out either ends and back in either ends.
Yeah. In metals, the charged particles responsible for the current are electrons, which move randomly at high speeds, even with no applied voltage. A direct current is produced when the electrons all drift in one direction, whilst continuing the random motion. I swear I've already read this out.
Yes, you have.
It's just got it on a different slide. Alternating currents. You will see it as a sinusoidal graph.
Suicidal graph.
Which is a sine graph, basically, which is just wiggly. All you need to know is that the line in the middle, or the sort of the average,
axis.
the axis, the x-axis, if you like, is time, and then you've got voltage on the y-axis. The highest point is the peak voltage, which is represented by V0, and the lowest point is minus V0, minus peak voltage. And then the time period is the period for one whole wave. And then frequency would be the number of cycles per second, which is F equals 1 over T.
1 over the time period it takes for a whole wave.
The peak-to-peak voltage is basically the same as the equivalent DC current voltage, whatever. Yeah. So you do that by 2 times V0.
Which is the peak voltage.
Which is peak voltage. And then peak-to-peak voltage, sorry. And then the root mean square is the equivalent to the DC values that produce the same power. This is worked out by the equation root V peak voltage squared divided by 2, which becomes
peak voltage divided by the root of 2 gives you. So if you
my mouth stopped working.
Thank God. So in the exam you'll be asked a question: calculate the RMS or check the RMS value of this AC power supply all you need to do for that, there is a lot of work behind how to figure out
Just ignore
how
that,
to use
just do
that.
the equation.
All you have to do is divide the peak voltage, which is the highest point on the
On the graph.
on the
The top bit.
the waveform, and then you divide that by √2 to give you the RMS value, which stands for root mean squared, but has no real doesn't really matter.
You can do that for
RMS.
voltage or for IRMS, which is current root mean squared. They're exactly the same. Just use the current
instead of the voltage.
Is that output V0? Peak current. It
Yes.
looks like output. Peak current, peak voltage. Right. You can calculate the. I'll do that in a minute. Yeah, for that, if you get complicated questions with oscilloscopes, I tell you what, we'll come to that in a little bit. It's just AC power. You can calculate the power delivered in alternating electricity using the same equation, P equals IV, but always use the root mean square values for voltage and currents in any equation that is used to calculate the average power delivered by an alternating electricity supply. God. Or, if given, use the peak values. Whatever one, they must be the same throughout the equation. An additional point is that mains electricity uses 50 Hz of frequency and 240 volts?
230, I think.
230 volts. You have to know that, because it might come up.
Yeah.
Do you want to simplify that, because I said it very quickly?
Right, basically, the reason you don't use... There's an equation, P equals IV, which is very useful in direct current supplies, but if you try and use that in an AC supply, the average voltage in particular will always boil down to zero because
it's of the negative bit.
because the wave goes above zero and below zero. It's alternating current. So use the root mean square value to give you a constant positive line, so you can use this equation. So it boils
a good
down
way to think of it, I like to think of it, is like a tide, like a wave. Imagine a stone on a wave. As a wave comes in, it pushes the stone, like pushing the current through. But then it recedes. It doesn't take the stone with it, so the current's still moving in a forward direction. But it is oscillating. The electrons are oscillating within the wire. However, the current is still flowing around the circuit in one direction. It's just the things inside it are moving forwards and backwards, if you like.
Yeah.
Is that right?
Yeah.
Is that a nice way to think about it? About right.
It's an easy way.
Just oscilloscopes is the last thing we're going to do, or cathode ray oscilloscopes, same thing, CRO, old crows. There are two main controls. All you need to know about, there are a hell of a lot of things, but just know about the time base, which is the time per division, and the voltage sensitivity. So time base is the x-axis, voltage is the y-axis. We've already touched on this. The time base controls the horizontal scale. I've just said that. Each square is one division. The setting tells you the time taken for the dot, if you like, to move across the square. Or move across one square. The voltage sensitivity is the vertical square. The setting tells you the voltage across each square. It is best to use to measure an alternating voltage as is able to display the entire waveform as a graph of voltage against time. One way that they might ask you a question is, how can you measure the voltage output efficiently? And you would simply say turn the time base off.
Yeah.
Because then you would just have you'd have a vertical line
From the peak voltage to the negative peak
and
voltage.
it's much easier to be able to tell the thing. So that's what you would say.
Also, you might need to know that a DC power supply, if I'm correct, is a horizontal line because there's no alternating nature of it.
Exactly.
So if you turned a DC power supply onto an oscilloscope, it would just be a horizontal line at the voltage that it specifies on the cell or the power supply. Mm-hmm. And if you turn the time base down to zero on a DC supply, it would just be a dot. Exactly.
And if you would, that's not worth saying anything else. Right, that's it for electricity. That's almost as long as the rest of the electricity topic. But never mind. Next time. Well, that's it for physics. We hope you do well in your exam.
Good luck.
I do, though, hope that I do better than you. So, sorry, Connor's mum. Sorry for that.
She's not doing physics.
Is she?
No.
Oh.
What a shame. Sorry, man, this has been wasted on you. Thanks for wasting your life.
Sorry.
Nah, it's alright. Good luck with the exams.
Thank you.
Bye.
Bye.